Okay, we are going to be talking about what are called tangent line approximations. So let me go ahead and write that in here. Tangent line approximations. So what in the world is a tangent line approximation? So let's look at this definition first. It says let f, or it says if f is differentiable at some point x equals a, then the approximating function L of x equals f of a plus f prime of a times x minus a is the linearization of f at a. The approximation is that f of x is approximately the linearization of x. So this is what they call standard line approximation. I call it tangent line approximation, but it's the same thing, okay? And they say, most importantly, that the point x equals a is the center of the approximation. So what in the world are we talking about? So if you see here, there's this blue function, and in this case, it's y equals the square root of 1 plus x. So suppose you wanted to know what the value of, I don't know, if you plugged in 3 in here into the function, well, what's the y value at this point? Well, this one's pretty easy. 1 plus 3 is 4. The square root of 4 is 2. So it's actually 2. But what if you had a point like out over here, I don't know, 3.8, let's suppose. Well, that's a little bit harder to figure out. So what you could do is you could use what's called a tangent line approximation, and that is that you use the derivative in such a way that you come up with a linear function, okay? A linear function that will approximate that y value for you, okay? So in doing that, you take something complex like this right here and you make it a little bit easier by looking at a linear function. And I think a lot of us are really comfortable with using linear functions, okay? Plugging in something for x and then you get a y. So what happens is that if you were to zoom in like really close to this, okay, at that point it becomes what we call locally linear, okay? So that's where this tangent line approximation comes in, okay? So what we're going to do is we're going to look at a couple of examples of this quote-unquote tangent line approximation or standard linear approximation, and we're going to figure out what the function would equal at that particular point. And of course, you know, in some of these cases it's really easy to figure out this kind of stuff, but what we're going to do is we're going to generate in these two problems the linear function that would approximate it, okay? So that's what we're going to do here. So they say, in this case, find the linearization of f of x equals 5x squared plus 4x plus 1 at the point where a equals 2. So what I'm going to do first is I'm going to write out my linearization formula. And that is to say that L of x equals f of a, which is the function evaluated at a, plus the derivative at a, so the derivative evaluated at a, times x minus a. Okay, so first thing I'm going to do is just find what f of a is. So f of a means that I'm looking for f of 2. So I'm just going to plug in 2 into the original function there, and let's see what I get. Okay, so I plug that in there and I get 29. You can verify that on a calculator or doing the order of operations. Okay, now I take the derivative, f prime of x. So let's see what we get. Derivative of 5x squared is 10x. Derivative of 4x is 4. Derivative of 1 is 0. So my derivative there is 10x plus 4. Now it is necessary for me to find f prime of a, which is f prime of 2. And what does that look like? 10 times 2 plus 4. That gives me 24. Okay? Now I'm ready to find my linearization L of x. Okay? So that's going to be f of a, which I found to be 29 from up above. All right? Plus, and then I'm going to take my f prime of a, which I found right in the previous step to be 24 times x minus, and a again was 2. And so I plug that in there, and this is basically my linearization, but of course I can simplify a little bit. So what does it look like? 29 plus 24x minus 48. That all simplifies to 24x minus, what is that, 19. So my linearization, L of x, equals 24x minus 19. And that's it. That there's nothing more to it. But what this tells us is that we can approximate the y value by plugging in a is 2 into the linearization, and that should be relatively close, if not exactly the same in this case, as what would happen if you had plugged in 2 into the original function, right? And that's because we're using the tangent line approximation, all right? It makes much more sense in application, of course, but there's really nothing to it when we're looking at these examples. So hopefully that was helpful. Let's take a look at another one, slightly more advanced, slightly more challenging, and I think you'll get the hang of it really quick if you haven't already. All right, so again, here we're going to take the linearization. So let me write that formula up again here at the top for you. Okay, f of a plus f prime of a times x minus a. That's always important. Keep that formula fresh in your mind. And then the other thing we're going to do is rewrite f of x. So let's say that f of x equals 6x plus 64 all to the 1/2 power. Now the reason for this is because we're going to have to take the derivative, and we're going to apply the power rule and the chain rule there. Okay, so let's take a look here, and the first thing we need to do is find f of 0. So f of 0, that's pretty simple here for us. That's the square root of 6 times 0 plus 64, which is the square root of 64, which is 8 in this case. All right, and then we take the derivative of the function. So we're going to bring the 1/2 down. We're going to multiply by the original function, 6x plus 64, but now to the negative 1/2 power because we have to subtract 1. Okay, and then by the chain rule, we multiply by the derivative of the inside, which is 6. So then you end up with something like this, 3 times 6x plus 64, because 6 times 1/2 is 3, all to the negative 1/2, and you can certainly clean it up. What does it look like? 3 divided by the square root of 6x plus 64. Now there's no real need to rationalize the denominator because we're trying to get an approximation anyway. So we're going to evaluate now the derivative at the point a, which in this case was 0. And that's a nice number there, 0. So when we plug that 0 in, you'll see right away what we get. We get 64 in the denominator, or square root of 64 I should say, which is just going to be 3 divided by 8. All right, and there's not much more to this because we now do the linearization, and the linearization will say, well, you take 8 plus 3 over 8, which was your f prime of 0, times x minus 0, but that's just 0 there when you multiply the 3/8 times 0. So you end up with 8 plus 3/8 x, which normally we would write like this in slope intercept form. But that right there is our linearization, and that right there will help us approximate the tangent, or well, approximate the y value anyways. So really neat. I mean, when you plug in 0, you know you're going to get 8, and when you plug in 0 up in the original, you do get 8. So it's actually spot on in this case at approximating the y value, and that's the whole concept behind this tangent line approximation. It will approximate the value of the function at that given point in time. Okay, so definitely an interesting topic here, linearization. we're going to move on in one of the next videos talking about differentials, but good stuff here. As always, I hope this video was helpful, and remember, like and subscribe.